be the first lecture out of chapter 4. So this chapter 4 deals with solutions and different types of chemical reactions. And so to start off with, we cover this concept of electrolytes and ionic reactions. So if you set up an experiment like this, you have a beaker with water in it, and hook up, put a couple of wires into it, connected by a battery and a voltmeter, and then you measure the current. So if this is pure water, then there's no current. Okay, so then if you take that beaker and you add something to it like sodium chloride. So the sodium chloride dissolve in water. Sodium chloride, of course, is table salt, and it will dissolve in water. So NaCl, if you remember, is really Na plus and Cl minus. It's an ionic compound. So when it dissolves in water, the sodiums and chlorides separate from each other. So we covered this back in the last chapter, chapter 11. So you know what the sodiums would look like. They would be surrounded by water molecules with the oxygens pointing towards the sodiums, and the chlorides would be surrounded by water molecules with the hydrogens pointed towards the Cl minus so that they could hydrogen bond with each other. But the point is that they separate. So you have free sodiums and free chlorides floating around in solution. So it ionizes. Right, that just means when it dissolves, the cations separate from the anions. And so now if you took this and you measured the current in this solution, once you add the sodium chloride, right now you would have current. So this solution would conduct electricity. All right, so how does that work? Why does it conduct electricity? So basically what's going to happen is the electrons are going to travel through the wire in one direction or the other. So one of the wires would be losing electrons, and the other wire on the other side of the battery would be gaining electrons. And so that's the current through the wire, is the movement of electrons. And so how does the current move through the solution? So if the wire on the left is losing electrons, then it's going to become positively charged. And if the wire on the right is gaining electrons, it's going to become negative charged. And so, of course, sodiums are positive. They're going to be attracted to the wire that's become a negative charge because it's gaining electrons. And the chloride, since it's negatively charged, it's going to move to the other wire, since that wire has become a positive charge since it's losing electrons. And so now the current is completed in solution. So in the wire, the current is the electrons moving, and in the solution, it's the sodium and chloride anions that are moving. So the sodiums would be picking up electrons, and the chlorides would be dropping off electrons at the positive wire, and then that would complete the circuit. Okay, so any compound that dissolves in water to give a conducting solution is known as an electrolyte. So this is probably a word that you've heard before. So where have you heard the word electrolyte used before? Probably in something like Gatorade. So if you look at a sports drink, so what's going to be electrolyte? Something that dissolves in water and ionizes in water, so it's going to be an ionic compound. So electrolytes are typically then ionic compounds that dissolve in water. So if you looked at the ingredient list on Gatorade, for example, it would probably have something like potassium chloride, which when in water, it's going to ionize to potassium ions and chloride anions. So potassium, of course, being one of the vital cations needed to sustain life. Okay, so what if you did the similar experiment? So set up another beaker with pure water, but this time you add glucose. So glucose, of course, is a sugar. It dissolves in water. If you look at the ingredient list of Gatorade bottle, it would also contain sugar in it. You know, what's the purpose of the sugar? Just to sweeten the drink, to make it taste better, I guess. So if you add glucose to water, so we looked at this in the last chapter, what does glucose look like in water? Right, it's a pretty complex molecule. So let me just sketch it again right quick. So glucose dissolves in water, but then if you check the voltmeter, right, there's no current. So it's not a conducting solution. So glucose would be an example of a non-electrolyte. So a non-electrolyte would be anything that dissolves in water. But gives a non-conducting solution. You know, so why doesn't glucose give a conducting solution? Because it does not ionize in water, right? So it doesn't split apart into cations and anions. It stays together as an intact molecule. Right, so there's no positives or negatives, so there's nothing that would be attracted to a positive wire, nothing that would be attracted to a negative wire. And so, of course, in the last chapter, we looked at what does glucose look like in waters, how does it interact with water, why is it water soluble? And that's because the oxygens are partial negative, so they would hydrogen bond to water. So all of the oxygens in the molecule would accept a hydrogen bond from water. And then all of the hydrogens are partial positive. So they would also hydrogen bond to water to the partial negative oxygens. But there's no positive and there's no negative still. So nothing to migrate in solution to the positive and negative, to a positive or negative wire, so the solution can't conduct electricity. Okay, so this is one thing that this chapter tries to do, is what do solutions look like at the atomic level, at the molecular level? Okay, so some basic definitions. So you should know what electrolyte means, what a non-electrolyte means. Solute. So what is the difference between a solute and a solvent? So the solute is the compound in a solution that is present in lesser amount. So in previous two examples, then that would be the NaCl or the glucose. And the solvent so solution is a solvent plus a solute, and the solvent is the compound in the greater amount. So of course in the previous examples that would have been water. Okay, so you can have an unsaturated solution, or a saturated solution, or a supersaturated solution. So an unsaturated solution would just mean that the solvent doesn't contain the maximum amount of solute that it could. It could dissolve more still. Saturated solution, so this would be like if you just add a little bit of solute, such as NaCl to water. If you add a lot of NaCl to water, Then at some point it stops dissolving, and then you have two phases. You have a solid phase, solid sodium chloride that did not dissolve, and the aqueous phase, the solution, the sodium chloride that is dissolved in water. All right, so you have a solution and a solvent, or salt and a solid, both present. It doesn't have to be solid, it could be a separate liquid that didn't dissolve fully in the solution. So then you can make what's called a supersaturated solution. So if you took this solution that was saturated and heat it, and then it reaches the point where all of the solute is dissolved, and then you cool it. Cool it back to room temperature. And if the solute stays dissolved, then now the solution is technically holding more solute than it should hold at that particular temperature, so you have a supersaturated solution. And this is an unstable solution. If you agitate it just a little bit, it could cause the excess solute to precipitate out. Okay, so that's some basic terminology that you should know. Okay, so moving on to molecular equation and ionic equation. So a molecular equation just shows what goes into a reaction and what comes out of a reaction, but doesn't try to depict what the actual solution looks like at the molecular level. So an example would be so calcium hydroxide plus sodium carbonate, both dissolved in water, so they're aqueous, react with each other to form calcium carbonate, solid, so that means it would precipitate out of the solution, and NaOH, aqueous, meaning the sodium hydroxide stays dissolved in solution. So that would be a molecular equation. It just tells you what went in. Calcium hydroxide and sodium carbonate went in. And then it tells you what came out of the reaction, right? Calcium carbonate and sodium hydroxide came out, but doesn't tell you what the solution actually looks like at the molecular level. So that's what an ionic equation tries to do. It tries to depict what does the reaction look like at the molecular level instead. So if you could see all of the atoms in the molecule, what does it actually look like when it's dissolved? So we'll take the same reaction. So calcium hydroxide is aqueous. So that means it dissolved. So what does this solution look like? Well, it's an ionic compound. So that means it ionizes in water. So here you have to recognize CaOH2 is going to become, in water, calcium 2 plus cations and hydroxide anions. So for every calcium hydroxide that dissolves, you get 2 calcium cations floating around, and you get 2 hydroxide anions floating around in solution. So, okay, let's get this out of the way. And then let's do the same for the other compound. So then sodium carbonate. So it's aqueous, so that means it dissolved in water. So when it dissolves in water, it ionizes. So you get 2 sodium cations, right? Because of the subscript there. So you don't get an Na2, right? There is no Na2. There's 2 Na pluses. And you get the Cl3 is carbonate. And of course you should hopefully memorize back in chapter 2 the charge on these things. So carbonate is 2 negative charge. Okay, so when sodium carbonate dissolves in water, then you get every single sodium carbonate that dissolves, you would get 2 sodium cations floating around, and then you would get a carbonate. And based on what we covered back in chapter 10, you could draw the Lewis dot structure for carbonate if you really wanted to know what this looks like at the atomic level. So if you sketched out the Lewis structure for carbonate, right, you would get that. Okay, so there's 1 carbonate and 2 sodium ions floating around, not attached to each other in solution. Of course, each would be interacting with water molecules. So if you really wanted to know what this looks like at the molecular level, then you would need to sketch in how would the carbonate interact with water. All of the oxygen, since they're negative or partial negative, would be hydrogen bonded to water molecules. Right, so each oxygen's lone pair could hydrogen bond to a different water molecule. And then all the sodiums, right, well, water molecules would surround all of the cations with the oxygens pointing towards the cation to make what's called ion dipole. Attractions, and these would be hydrogen bond. So at the molecular level, that's what sodium carbonate looks like in water. You could do the same thing for calcium hydroxide. Right, all of the calciums, ions would have water molecules around them with the oxygens pointed toward them, and the hydroxides would all be hydrogen bonded. So oxygen, hydrogen bond to a hydrogen of water, and hydrogen, hydrogen bond to an oxygen of water. Okay, so the ionic equation then tries to represent what the solutions actually look like in solutions. So in solution, you have, for every calcium hydroxide that dissolves, you have a calcium 2+ ion, and you have 2 hydroxide anions separated from each other. And for every sodium carbonate that dissolves, you have 2 sodium cations and 1 carbonate anion. Okay, so now what you do is you take those 2 solutions and mix them. So we're going to take this solution and this one, and we're going to mix them together. Okay, so let me write the chemical equation again. Okay, so in this case, the calcium carbonate is solid, so that means it did not dissolve. So what you're going to have is calcium carbonate precipitate. So you mix the two solutions together. Initially, they would both be homogeneous, and then when you mix them together, then you would see a precipitate starting to form. So it would probably become very cloudy, and over time, that solid would precipitate or settle to the bottom, and you would have calcium carbonate on the bottom, not dissolved. But the sodium hydroxide is aqueous. So it's still dissolved. So what does sodium hydroxide look like in water? Well, you would have for every sodium hydroxide that's dissolved, you would have one sodium cation and one hydroxide anion. And if we just balance the equation, right, so we had one calcium and two hydroxides, so there's still two hydroxides floating around. And we had two sodiums and one carbonate, so the one carbonate went with the calcium to make solid calcium carbonate, but there's still two sodiums floating around. So to finish the ionic equation then, so anything that's solid, liquid, or gas in the molecular equation is not going to be ionized, and so it's going to stay together. But the sodium hydroxide is aqueous, so it's still going to be split apart. So two sodiums plus two hydroxide. And then that would be the ionic equation. So let me just write it here again, a little bit clearer. Okay, so this would become calcium 2 plus aqueous plus 2 hydroxide aqueous. That means they're both dissolved, both ionized, plus 2 sodium plus aqueous plus carbonate, one of those, aqueous. Okay, so since there's two of these, then that is going to go there, right? Two hydroxides. And since there's two of these, that's going to go there. And since this is solid, so if it's solid, liquid, or gas, then you're going to keep it together in an ionic equation. So this is still then not wrote in the ionized form. Keep that together. And then 2 Na plus aqueous plus 2 hydroxide aqueous. Okay, and then you have what's known as the net ionic equation. So it only shows the things that changed. So if you notice, the hydroxide didn't change, the sodium didn't change, the calcium changed, and the carbonate changed because they got together to make that. So that's the only part that, so the net ionic equation only shows the things that changed. So that would be the net ionic equation. And then lastly here, another definition, you have what are known as spectator ions. So this is the things that did not change. So that would be the sodium. Nothing happened to the sodium. It was just watching in the reaction, and nothing happened to the hydroxide. All right, so if you take the net ionic equation, the things that did not change in that equation would be what's called the spectator ions. Okay.